Hi, in this video we'll try to use the Stefan-Boltzmann law to solve two questions, which is 8.8 and 8.9. So if you haven't done it, pause the video now and we'll go for it together.
A few moments later.
So the first question is asking you the power emitted by body, of course talking about the radiation, will change when the temperature is increased from 100 degrees Celsius to 200 degrees Celsius. As usual, if you know me, I would like to show you the wrong answer, and so probably will keep you more mindful in the future. Wrong answer number 1. So I know the temperature increased from 100 to 200, so that is 2 times, and if temperature increase, power increase, so 2 times that. Wrong answer number 2. So I actually remember just now the equation of Stefan-Boltzmann law is this one, and so it's t to the power 4. So if this is 2 times greater and it should be 2 to the power 4, that means how much is this? 4 times 4, so that means it is 16 times greater. The correct answer. Alright, when you try to use the Stefan-Boltzmann law, there is a variable called temperature T. Similar to ideal gas law, when you try to substitute T into it, you have to use the units of Kelvin. So that means if you want to find the power ratio, that means you can use P2 over P1, and you can substitute the things that you know. Actually you don't know, but then they are constant, so I can keep it like this. But for the T, then I have to do 200 plus 273 to the power of 4, and same for the one that is below, 100 plus 273 to the power of 4, and then of course all these things will be cancelled out, and then you can use your calculator to find out the answer. So I will do 200 plus 273 divide, well actually I can do it 373, and then you'll find out 1.26, something like that, and then you can just press to the power of 4. So the answer is actually 2.58588 something, and I will round it up to 3 sig fig, so 2.59 in this case. Okay, so that means when you increase the temperature by a double, the power doesn't increase by a double, it's more than the double. Wrong answer again. So we will be using the equation, and then we would just substitute what we want. So E is 0.9, the constant we can find from the data booklet, which is here, 5.67, and 8, 10 to the power of 8, or negative 8. Yes, negative 8. Okay, and then for area we know it's 1.6, and for temperature this time, yes, I know we have to use the Kelvin scale, but then since we have 37 degree and 0 degree, then we can just do that, and then we will be able to find out the difference, because when you change to Kelvin it's all the same, right? Then we should be able to find the net power by using calculator. The answer is 0.153, right? So this is in the answer of what? If you multiply it with 30 and 60 because of 30 minutes, you can then find the answer. Am I right? The correct answer. No, you can't do it that way, because when we try to apply the Stefan-Boltzmann law, it is either calculating the power of radiation that is going in or going out. You can't just merge them together with the temperature like this, because if you think about the net powered that you can try to calculate, what you actually do here, right? You're actually mostly wrong, but then what you could do is 37 plus 273, changing to Kelvin first, to the power of 4, and then you can do minus 0 plus 273 to the power of 4. And obviously this is different from just minus each of them and then to the power of 4, obviously. So your answer should then change to about 300.5 in total, and that is round up to 3 sig fig, I say. 301 watts. So if you want to calculate the energy in 30 minutes, you just have to times 60 and times 30, and you should get the answer as 541800. So about 5.42 times 10 to the power of 1, 2, 3, 4, 5 joule in total. Okay, but do we actually know like whether or not this is significant or not then? This is the best part of this video which I'm looking for. So let's say you kind of like do this exercise, so you lose that much of energy to of course your surrounding by that much we calculated. So how many cans of Coke is it equivalent to then? So it's like you do the exercise and maybe you eat more food, then probably the efforts that you do for the exercise will be wasted. So how much would that be in terms of the Coke? Maybe you can make a guess. 1 can, 2 can, 3, 4, 5, or 10.
A few moments later.
Alright, so this is a website called coca-cola.co.uk. It seems to be one of the official websites. So it said for a can, standard can 330 ml of Coca-Cola original, there will be 139 calories there inside, and so we wonder how that would be converted to SI units. So we can say here it's at 0.581 kJ. So that means it's 581 joules only. But then if I think about these, then it doesn't make sense to me. That means you can actually drink like what? You can drink like 100 can? No, right? No, 1,000 can, which I don't think is correct, right? It's so strange that this number is so small. I don't really think that is correct at all. So I try to look up like different labels again, or maybe from different sources. Here I find there's a label saying that for this can, again 330 ml, and in terms of energy, it's actually 139 calories. Alright, so I really have no idea why there's a missing K there, right? Even this is supposed to be a official website, but anyway, and that is to say, the energy that it actually takes is not 500 something, right? It's not 581. It's actually about 594 kJ. So if you plug in back to our number here, so the number of cans should be the total energy. So this one divide 594 kJ, so 330, and that is, wait, not even 1 can. Unfortunately, you can only do about 0.91 can, which if you try to multiply with the volume, so-called 330, so that is going to be 301 mil only, right? So, or if you use SI unit, cm cube, so not even 1 can of Coca-Cola. That is horrible, because think about how much torture, how much pain it takes to stay in the ice for 30 minutes. Remember, you are naked, and all you get to drink equivalent without gaining any fat will not even be 1 can of Coca-Cola. Horrible. That's all. So in this video, you should have learned how to apply the Stefan-Boltzmann law to do calculation. And 2 things you should pay attention. One is when you substitute into the temperature, you should use the Kelvin scale. The second thing is when you try to find the net energy or net powered, you can't just minus the temperature directly. You have to calculate to the power of 4 first, and then minus another temperature to the power of 4. I will see you again in the next video.